Okay, so in this last video on modular arithmetic, I'm going to be talking about powers of units. Now, in the previous video, I explained exactly when an element of Zn is a unit. It's when the GCD of that element, or the representative, and n is equal to 1, so that's when they're relatively prime. I also described when Zn is a field. It's a field exactly when n is a prime number. And being a field means that everything except for 0 is a unit. Everything except for 0 is invertible. So I'm going to start with some basic facts about units, and then I'm going to start talking about powers of units and some powerful theorems that we have at our disposal for looking at when the power of a unit is equal to 1. So let me start off with some basic facts. First, the product of two units i.e. invertible elements in Zn is again a unit. This is pretty easy to see if you have if A and B are your units. Then if you take A times B, and you multiply that by A inverse and B inverse, then what you're going to get back is just 1. So A times B is a unit. What this tells you is that all powers of unit are also units. So you multiply two units together, you get something that's invertible, something that's a unit again, and if you take something that's a unit and you multiply against itself, then naturally, again, it's going to be a unit. So the question is, can you ever raise a unit to a power and get the identity element? And so the answer is this always happens because of the finiteness of Zn. So, so for every unit A inside Zn, there exists some integer m with A raised to that integer m. It's going to give you the converse class of 1. So what's the proof for this? I want you to consider the sequence. Starting with A, then squaring it, then cubing it, and so on. Now the trick is, this is an infinite sequence, but there's only finitely many elements in Zn. So as there are only finitely many elements in Zn, there must be repeated elements So, there exist some integers k strictly less than L. So there's two integers, k and L, which are different, and they have a to the k has to be equal to a to the L. So here are the two indices, or the two exponents rather, where the powers become equal. So our next step is we multiply by a to the minus k. So you might be asking yourself, what is a to the minus k? We know a to the minus 1 is the inverse of a, and we're assuming that a is some kind of unit. So we know that there is an inverse. Take that inverse and raise it to the kth power, and that's what I mean by a to the minus k. And you'll realize that this is actually an inverse for a to the k. So what do we get? To obtain, multiplying through, that's an inverse for this. This is a multiplied by itself k times. This is the inverse k times. They'll cancel each other to give you just the identity back. And when I multiply these two, the exponents add nicely. So it's going to be L minus k. And this is exactly what we wanted to find. So here's an exponent. M equals L minus k with a to the M is 1. So some power of our element gives us 1. Some power of our unit gives us 1. What we want to do now is we want to try and answer the question of what exponent you have to put on a given element in order to get 1 back. Now, it's a little much to ask that question because it depends on the particular element you have, right? For instance, if you start off with the element 1, then raising 1 to the 0, or rather say 1 to the 1, will give you back just 1. Whereas if you have some other element, if you have, say, the congruence class of minus 1, then 2 will work. And so it depends on the congruence class, what exponent you need to raise it to give you 1. However, we have some theorems which tell us uniform results, which tell us specific numbers which will work for all elements at the same time. So let me write down Fermat's little theorem. So this is Fermat's little theorem. If P is a prime, and A in ZP is non-zero, then A to the P is A. So let's understand what's going on here. First off, I'm assuming that P is a prime and we're working in ZP. That means if I say that the congruence class of A is non-zero, then it's invertible, right? We know ZP is our field. So A is definitely a unit here. And we're saying that if we take this unit and we raise it to the power P, well, we will get back A. So it follows from, let me say, Fermat's little theorem that A to the P minus 1 is the congruence class of 1 in ZP. So that answers the question that we were asking. What power can we put on an element to give us 1? And notice this doesn't depend on what A is. This happens for all elements for the exact same exponent. Now, I'd like to write this down one more time, just using modular arithmetic, because I think that's how you'll read it if you see it in other places. So, in terms of, let's say, of congruence, what we're really saying is a to the p is congruent to a mod p, where a is not 0. Where p does not divide a, and p is prime. That's the same thing as the congruence class of a being non-zero. Okay, so let me use an example of the power of this theorem. So the question is, why don't you compute the remainder of, let's do 9 to the 1, 2, 3, 4 upon division by 11. So this is a really large number. We want to do our long division by 11. Let's see if we have some algebraic way of figuring out what the remainder is going to be. So the first thing is, by Fermat's little theorem, what do we know? We know that, first off, 9 is not 0 mod 11, right? So we know that 9 to the 11 minus 1, we know that 9 to the 10 is congruent to 1 mod 11. And so this is the relationship that we're going to use to simplify this and simplify all the modular arithmetic. So what is 9 to the 1, 2, 3, 4? So I want to say working mod 11. Let's break it up. 9 to the 1, 2, 3, 4 is, well, it's the exact same number as 9 to the 1,230 times 9 to the 4, which is the exact same number as 9 to the 10 raised to the 123 times 9 to the 4. Now you see how we're going to use Fermat's little theorem. 9 to the 10 is congruent to 1. So this term vanishes, and we're left with 9 to the 4. And now we just have to do a little bit of arithmetic. We're working mod 11, right? So this is 81 squared, right? 9 squared squared. So 81 mod 11, 11 times 7 is 77. And so this is 4 more than that. So I'm going to say that 81 is congruent to 4 mod 11. So this is 4 squared, and that's 16, and 16 mod 11 is 5. So to conclude, the remainder of 9 to the 1, 2, 3, 4 after division by 11 is 5. All right. So I'm going to pause the video there in case I go over time. All right. I just want to make a few more comments before I stop. So the last comment I want to make is that Fermat's little theorem is just a stepping stone away from Euler's theorem, which is much more general because it doesn't restrict us to working in ZP, where P is prime. So Euler's theorem. So if a congruence class in Zn, and now n can be any number. So if a congruence class is a unit, then a to the magic number n is congruent to 1. Now what is this magic number? So phi of n is the number of units in Zn. So it's the number of invertible elements in Z, the number of things which have GCD with n giving 1. So the number of elements that are relatively prime to n. And so this is this can be a tricky number to compute. In fact, a lot of cryptographic systems rely on this being difficult to compute, even if you know what n is. I'll say more about that in a second, but let me rephrase this in terms of congruences. So, rephrase in terms of congruences. How do I interpret this? Well, instead of working with a congruence class and asking that to be a unit, I'm going to take an integer and say if this integer has GCD of a and n be 1, so if it's relatively prime to n, then a to the phi of n is congruent to 1 mod n, where phi of n is the set of all r integers such that 1 is less than or equal to r, strictly less than n, and the GCD of r and n is 1. Oh, and I want it to be the size of that set. So this is just the collection of all units. Right, I'm going through all the elements, I'm skipping 0, because I don't want you to think about whether the GCD is something with 0 is equal to 1 or not. So we're going through all units, we're collecting them up. This tells us that they're units, we count them, and that's giving us phi of n. And so it's the exact same formula as you see before, though this is kind of more typical for what you'll see in a textbook. People like to use this congruence as opposed to talking about elements of Zn. So one last thing I wanted to say was that Euler's theorem forms the backbone for a cryptographic system called RSA. So RSA was made in the 70s. It's I want to say it's one of the few secure cryptographic systems, or one of the few cryptographic systems that we think is secure, based on recent revelations from all the NSA documents in the US. It seems like a bunch of cryptographic systems are open to attack. A cryptographic system based on Euler's theorem and using exponentiation to kind of revert a message back to its original form after being encoded seems to be the most secure kind of encryption that we have. And it's not too hard to actually understand what the algorithm is doing. So if you want to go to the Wikipedia page for RSA, you may be able to go through how it's constructing the keys and how it's encoding and decoding messages. And based on just the knowledge of Euler's theorem, you can probably figure out why it's working. The underlying security is that computing phi of n is very difficult for anything that's not a prime. And so it requires factorization of n, and factorization is an incredibly hard algorithm. You can imagine really, really large numbers which people can't factor and use them for your cryptographic scheme. So I haven't proved Euler's theorem and I haven't proved Fermat's little theorem. What we're going to do is we're going to come back to these, and they're going to turn out to be incredibly easy theorems once we have our hands on a little bit of basic group theory. And so we'll use group theory to justify why these relations hold.